Thank you, everybody. How's everybody feeling? Yeah, good? Hopefully a good start to your reInvent? Well, thank you so much for taking time to come listen to us talk about the quandary of containerized machine learning. I know that I'm eating up valuable drinking and eating time from you all, so it very much is appreciated that you would take 20 minutes to come listen and learn a little bit. So, you see the title of our talk today. It's called The Quandary of Containerized Machine Learning. You might wonder, well, what is the quandary? I'll get to that. I'd love to be able to share with you a little bit about some of the challenges that we've faced in using containers and how we've solved some of those problems to really scale up our machine learning efforts, specifically with the use of containers. So before I dive too deeply into things, just a little bit about us. So my name is Alan. I'm an associate director at BCG Gamma. And so we're part of the Boston Consulting Group. How many of you know the Boston Consulting Group? So in the business world, this is actually quite a well-known company, but in tech circles, a lot of people really have no idea who we are, so I need to kind of just lay some foundation for you all. So we're a global strategy consulting firm, and we're from BCG Gamma, which is the AI consulting part of the company. So any of our clients that need AI use cases to be done, BCG Gamma is the group that we call upon. And so a few examples of clients that we support, one of which is Starbucks. Who here has ever ordered a Starbucks drink off of the app? Okay, a good number of you. And you know how when you order on the app, you get these reward stars, and then you can redeem them for free drinks and food later? So BCG Gamma actually built the model that does the entire loyalty system for Starbucks. And so when you get those star challenges that say, hey, next week, go buy 2 Frappuccinos if you want 50 stars, it's because a model in the back end that we developed is actually personalizing those offers to you one-to-one. It's not a marketing person in Seattle deciding that next week you should go buy 2 Frappuccinos. It's based on the model. And so another example of some work that we do is we also schedule all the flights for KLM Airlines. I don't know if you guys have ever flown KLM Airlines, but we built the entire scheduling system for them that does routing, airplane scheduling, gate assignments, crew assignments, and so forth. And then we also work very closely with the Gates Foundation to do modeling around disease eradication. So that's just a very small vignette of some of the work that we do. We're all over the world, and we do quite a lot of work with a variety of clients. So getting into the meat of things, before I can talk about why it's hard to use containers for machine learning, I need to set up a little bit of foundational knowledge. So I don't know how much all of you are deeply familiar with machine learning, but just to set the stage here, machine learning is the process of leveraging statistical models to be able to predict outcomes based on prior data. And so if you look at this diagram, what you have is you've got training data, which are events that you've observed, and then you move them into a machine learning algorithm, which then produces a model. Once you have a model, you're able to take some new input data to produce predictions, and then you can evaluate whether or not those predictions seem accurate or not. And you can go through a few cycles of this train and evaluate before you end up with a trained model on the outside, right? So pretty straightforward. But unfortunately, having a trained model by itself, I think if any of you are machine learning practitioners, by itself, a model doesn't do anything alone, right? You need to go through a second phase, which is making predictions. And so in order for you to take the model that you've trained in the previous phase, which essentially is just a bag of weights and coefficients, into something that does something for real, you need to wrap it with an application. And most commonly, people might turn this into either a batch job that you might schedule on a daily basis, or you might do an API wrapper. For example, if you're in the Python ecosystem, you might wrap your model with Flask and turn it into a REST API. And so, for example, if you made a model that predicts flowers, you might be able to feed it flower measurements, have it go through the REST wrapper, which encapsulates the trained model, and then it spits out that this flower is supposed to be an iris versicolor, all right? Wow, they're loud. So what's the big problem? All of this seems relatively straightforward, right? Well, we're a company where we do a lot of use cases at scale. If you're from a software engineering background, containers are clearly something that's very, very popular in terms of helping scale because you can replicate workloads, you can automate and scale horizontally, especially if you use something like Kubernetes. And so we, as data scientists, wanted to be able to bring some of that know-how and some of those benefits from the containerized world into machine learning, but it actually poses a few problems for us. And so what are those problems? As I just mentioned, machine learning has two phases, right? It has the training phase and it has the prediction phase. The application that you use to make your prediction is actually highly coupled with the model that you trained, right? For example, the library that you read in the model must be the same version of the model that you use to train your model. If you make any assumptions about how you pre-process your inputs, how you do the pre-processing and the training must be replicated on the prediction side. So you have a tight coupling between training the model and using the model. But think about what happens in a container. You build a container statically before you do the runtime. So how do you build a container that itself is dependent on its own output at runtime? Does that make sense? Right? So you build in your training algorithm into a container, but how do you embed an application that's dependent on its own output to produce a complete application, right? So this is the quandary of containerized machine learning. So how would we solve this? Well, let's talk about a few naive approaches before we get into the meat of things, right? We could build a container, and when you launch the container, you can have it pull from S3 some version of a trained model into the container at runtime, right? But this presents a problem because you've now lost the versioning guarantee of a Docker container. If you launch Docker container v1 and you're dynamically pulling your model, you have no guarantee as to what's actually running in your container anymore. So you got to scratch that. It doesn't really work, right? The other thing you could do is, I guess you could train the model during the build phase, right? So you would bake the trained model into the container by actually making the Docker file do the training. But here's the problem, is then you have to bake in all your training data into the container as well. And so if you have a small training data set, maybe this is feasible, but do you really want your data also being deployed every single time you deploy your container? Probably not. And when you're talking about large data sets, this is actually entirely impractical, right? And so, suggestion 3. Maybe you train outside of your Docker build, and then you copy in the trained model during the build, and you kind of closely couple those. It's a little bit better, but it's really not so different than how you would take the model from S3. It's just that you happen to be training the model a little bit closer to where the Docker container is being created, right? And so now this brings us to the quandary. How do you solve this catch-22 of having something that at build time needs to depend on something that is produced at runtime for a container that hasn't been built or run yet, right? It turns out we can do better. And it's actually quite straightforward. So going back to our phase 1, right? Let's say that we have a container here. Let's call it C1, all right? We've got our training code here. And then we've also embedded the wrapper that does the predictions, right? This might be the REST API. And you'll notice that it has yet to have a model embedded into it. It is an application that has no model yet. And so it's kind of got a model-shaped hole there, right? But let's call this container 1. We can build this container, feed in the training data, and then have the training application portion of it produce the trained model. And then in phase 2, what we do is we actually take the trained model, we take the same C1, and then we just run another Docker build where the base of the image is C1, and all we actually do is simply take its output from the first execution and copy it back into itself. And so what you have is you have a C2, which you have strong guarantees that your application and code and your training code can actually be versioned in lockstep. If you make a change to how the data pipeline works in your training, you can make the atomic change to the application side and embed them into the same container, right? You have that strong guarantee still. But now what you do is you just take its own output, feed it back into itself, and create one incremental revision that is guaranteed to be the same, except for the addition of the model now. And so what you have is you've taken C1, which has this model-shaped hole, you've taken its own outputs, and then you've what we call hydrated the container, and now you've filled that gap, right? So I just want to take you through a real quick demo of how we do this in practice. So what we have here is a platform that we use in-house called Source AI. This runs in AWS. And this manages all of the training and data science lifecycle for our data scientists within Gamma. And so for example, I have a model here. When I go and want to create a train, this is hooked up to Git in the back end. And when I actually train something here, what it first does is it builds that C1. You remember that C1 container that I talked about? It takes the application and the training code and it builds it into a container that we can now execute in a training phase. So right now, what you see here is we've taken that container, we've built it, we've put it into EKS or Kubernetes or wherever you run your Kubernetes workloads, and it's now training the model. And so if you take a look at a run that's already been completed, you'll actually see that this model has outputted a few things. What we now do is as soon as your model is finished training, we run that phase 2 build where we take your C1, we take these outputs, and then we just layer them on top of C1 to create C2. And so now what you have is you've got your container from the original training hydrated with its own outputs to produce a secondary container that can now be deployed. And so when we actually deploy this, let's call this AWS 2, what it does is it takes that secondary build, it now deploys this as a service in your Kubernetes cluster, and then if you go over to your deployments, you'll find AWS 2, you've now got a URL, if you paste that URL in, so this is the model that I trained, but now seeded into its application. And the application that you see is a REST API with a simple front end on top of it. And so if you see that if I hit predict, you'll see that it thinks that this is an iris versicolor. If I change some of these numbers, you'll see that it now thinks it's an iris setosa. And so this application, which needs to be closely coupled with the training code that produces the model, is now versioned very, very tightly with strong guarantees, and now can be easily deployed into your production environment and scaled horizontally. And so that's pretty much all I have to share with you today. Hopefully you found this interesting and somewhat educational, and maybe it kind of gets your own creative juices going a little bit. The crazy thing about this is that this was a huge problem for us. When we came up with this approach, it's actually very, very simple and very, very elegant and seems almost trivial once you see it done, but it really does solve a lot of the quandary of putting containerized machine learning models into actual containers and doing them in a way that preserves the strong versioning and guarantees that you expect from containers. So if you want to learn more about this, you can find more about us at bcggamma.com, or you can learn about the platform that you saw called Source AI. You can go to source.ai.com. We're at booth 215, right around the corner. We've got cool swag. We've got friendly people who want to talk to you. We've got reusable straws. We've got pens. We've got cookies and whatever else we've got over there. So come by, say hi. If you want, you can talk to me directly. Just email me. It's chen.allen@bcg.com. I'd be happy to chat with you in person now if you want to email me later. I'd love to just have a conversation and just talk shop and see what you're thinking about. Are you using containers? Are you guys doing machine learning? Have you run into some of these problems? Have you done a similar approach? Anything that you guys are interested in talking about, I'd love to talk to you. And so thank you so much for the time. And if you have a moment, there's going to be a survey about this particular talk. And so if you liked what you saw, please rate it highly. If you didn't like what you see, don't put your data in because I don't want to hear about it. And so hopefully you enjoyed the talk and you found it somewhat educational. Enjoy the rest of your week at reInvent. A pleasure to have you all. Thank you for the time. Let me know if you have any questions. I'll linger around. All right? Thanks.